Check, check. Test. Roman, how are you doing?
I'm good. Yourself, Professor?
Good. You can hear me, see my screen?
Yes, sir.
All right. Yeah, so there's this online encyclopedia of integer sequences. So, you know how I was asking you to come up with your own sequences and stuff. So like generally, if someone gives you a sequence, it's pretty hard to figure out a formula. I mean, you can make these things pretty complicated, right? So this is an encyclopedia of them, and you can put a sequence in, and then you can do a search, and it'll bring up different like history behind the sequence if it's an important sequence at all. Let me see this one. Like, let me put this one in here. Some of you may recognize this sequence: 1, 1, 2, 3, 5. Anyone recognize that one? 8, 13. Anyone ever seen that sequence before?
Fibonacci.
Fibonacci, yeah,
Yeah.
this Fibonacci sequence. So they give you like a formula for it. Now, this is a different type of formula. We didn't talk about this. We haven't talked about this. It's called a recursive formula instead of an explicit formula. But anyway, you can come here and start looking at all sorts of, you know, all sorts of different sequences. Let me see if I can go back to this. No. Here. Anyway. I thought there was one where you could just like list out all the different sequences or just like have them all listed, but let's see. I don't see it. Yeah, this is the welcome page. So, oh, index, here we go, maybe. An index of the most important sequences. Here we go. So like when I did Fibonacci, here. Let's see. Fielder sequences. I have no idea what a fielder sequence is, but here it is. Applications. So anyways, there's this huge resource about sequences. I just want to bring that up because, again, sequences are just like functions. Any function you can dream up, you can dream up a sequence too. So, all right, let's get down to business. Gosh, how did it become 9:02 already? I sent out the take-home exam, and I hope that you've started on this. And if you haven't, that's okay, but you need to get going on it pretty quick here. The main thing I want to talk about was just, one thing that Christian asked here at the beginning of class was, I'm saying you can use graphing utilities to, do your graphs. And in fact, I would like for you to do that. But how do you actually put that into your work, right? So a lot of this is going to be about how you do that. If you want to make if you want your test to be fully electronic, where it's a PDF that you submit to me at the end, that's fine. But if you do that, you should be able to print it too. So, but I'm not real particular about what format you turn it in, just that you're nice, and it's like a project almost, this is about presentation of your ideas as much as it is the math. So I don't want to give things away, but here's my first, I've already done the solution. So just to give you an example of like what the first one looked like for me. So here's where the hell is oh, here it is. Okay, so the first thing I did is I went to Desmos and I graphed it, and it was messy. I had to adjust the windows and stuff so I could see where things were. Okay, that's part of this is, you tweaking things. And so I inserted that graph, labeled things, and then I went on and did my work. Okay, so I don't know how you do it in Word or what, everyone's going to have different resources. I do everything in OneNote, but there's other things. What was the other one?
I use OneNote.
OneNote, Evernote, so any questions on that? What the expectation is? Nice and neat and clean and in order. It's not like an in-class test. In-class test, I understand if it looks like crap, you're all over the place, your brain's all over the place. But when you have a test that you have time and you can make it look good, I expect it to look decent. Good. Questions on that? All right, so I said on that it's due on the due on the 13th, right? That's next. Sorry, what? Oh, exam 3, yeah, sorry. November 10th. So that's next Wednesday, right? So I will not be in town. I will be out of town next Wednesday. All right. So I've debated, should we have class? What should we do? I think what I'm going to do is the test is going to be due that day, right? I've told you can work in groups of up to 3. All right. So that day, if you want to work with your classmates, go to the lab or wherever, somewhere on campus and work together, that's fine. I'm not going to officially have class here. The test will be due. It's going to have to be electronic since I'm not going to be here. I thought about having you physically turn it in, but I think you're going to have to upload it to some, well, I'm using OneDrive now, not Dropbox. So I'll send you a link for that. But as far as class next Wednesday, we won't physically be here, but I might have an assignment for you to do at home, which would maybe be watching a video. It might be doing, a couple of exercises, something, right? But I think it'll be better to do that than have a sub. Because if we have a sub, I'll probably have to come in here and like explain, because everyone explains things differently. I'll probably have to re-explain what they did anyway. So I think we'll just take advantage of that being time for you to get the test done, right? What time did I say it's due? 5 p.m. So 5 p.m. that day, right? So that means you could come in here, you can meet with your classmates, you have the rest of the day to finish it, right? Questions? All right, let's do it. We're in November, right? So today is more about sequences, all right? All last class was you just kind of understanding the idea of a sequence, We looked at a couple of the common sequences. And let me make sure my pen is working properly here, okay? But I spent a lot of time this weekend putting together formal notes for this section because I've never had formal notes. I told you I like to kind of go, do it as I go, but I've started to put some formal notes together. I will send these out to you later today. And it just goes through, it defines, what a sequence is. We did that. What's the notation? The difference between an infinite sequence and a finite sequence. We are not interested in finite sequences here. All right. We are only really going to deal with infinite sequences. I talked about the common sequences, like a sub n is equal to n, that generates the sequence 1, 2, 3, 4. And then there's some other examples here. We did all this last time, but now it's going to be nice in your notes. And then I did alternating sign sequence, how we can get positive, negative, or negative, positive. And then other common ones. And then we started talking about, well, I didn't formally state what an alternating sequence is, but formally an alternating sequence is either going to be a sequence that goes negative, positive, negative, positive, or it's going to go positive, negative, positive, negative. And the way you can look at that is the sequence a sub n is defined to be, well, here's where we use that -1 to the n part to make it flip back and forth. And then the other part, whatever it is just some other formula that creates the rest of the sequence. So that's the general look of an alternating sequence that starts negative. And then this is an alternating sequence that starts positive. And I gave you an example. And I think we ended class talking about factorial, right? That was the last thing we defined, was what is factorial. I told you that factorial is defined at 0. 0 factorial is defined to be 1. Somebody asked me about that. Did you look into that a little bit or no? The gamma function?
Yeah.
So the factorial is really there's a larger function called the gamma function that the factorial is the gamma function, but only on integers. The gamma function is defined for all numbers. So if you're interested in looking more into that, it would help you understand why this has to be 1. And I gave you an example. And then the big property of factorial that we need to know is this one right here. Is this big enough for everyone? Should I go a little bit bigger on this? Or is that a little better? The other property, or the big property we need to know, is this one right here. N plus 1 factorial over n factorial. That what happens is if you write out what this is on top and bottom, a bunch of stuff cancels. And all you're left with is the n plus 1. And I did an example of that in class last time. All right, so that's where we were. All right, so now we step into the rest of this section. There's a lot in this section. All right. First, we want to look at visualizing a sequence. So how do we visualize a sequence? We can plot a sequence just like a function, but we just have to notice that when we do it, we're not going to get this nice, smooth, continuous curve, right? And we did talk about this last time. So I gave you an example here of an alternating sequence. Notice we have -1 to the n. So that's going to start us, that's going to make us alternate. We're going to start with a negative number here, right? Because we always start with n being 1. So we plug 1 in here for n, and we plug 1 in here for n, we should get -1. Then when we plug in 2, we should get a positive, and then 2 squared is 4, and then we should get a negative, and then 3 squared is 9. Yes? Okay, so if we were to plot this, here's what it would look like. Now, unfortunately, I'm going to have to go a little smaller again. This is what that sequence would look like, right? If you plug in 1, it's hard to see it here. When you plug in 1, you get -1. So that's down just 1. And if I plug in 2, I get 4, so up a little bit. If I plug in 3, it's -9. If I plug in 4, it's +16. If I plug in 5, it's -25. If I plug in 6, it's 36, right? So it alternates back and forth. So you get this graph, okay? So that is the plot of that sequence, all right? But the important thing is it's not nice and smooth and continuous like a function. Everything we've studied in the past has been nice and smooth, all right? Here I have something where we can come up with any sequence we want. I can type it in right here, and then it'll plot the sequence for us. So the sequence you see right now is n squared over 1 plus n squared. And so what would happen, let me write that down. Oh, I got to open a program. Hold on. Nope, that was right. This is n squared over 1 plus n squared. So the sequence here, if I plug in 1, what would I get? A half. Okay, what happens if I plug in 2? 4/5. One more, 3, 9/10, and so on and so forth, right? So here's the sequence. You plug in 1, you get half. You plug in 2, you get 4/5. You plug in 3, you get 9/10. Do y'all notice that no matter how far we go out, it looks like this thing will never go past 1. And you can kind of tell by what's happening here, right? The denominator is always 1 more than the numerator for this sequence. So let's take a look at some more points here. If I do more of these, see? So no matter how far I go out, they seem to be bounded, right? They seem to not go past something. In fact, they get closer and closer to something, right? They get closer and closer to 1, would you say? They never get there though, right? Never gets to 1. This is important, all right? This is a very important idea here today, is this idea that it never got somewhere. So now we start talking about what's called the limit of a sequence. The limit of a sequence. We did limits of functions, right? Back in calculus 1, we took the limit of a function, but now we want to know what the limit of a sequence is. So we need to define it first, right? So given a sequence a sub n, we will say that the sequence has a limit of L if we take the limit and we let n go to infinity. So remember, n is the subscript, right? The subscript on this function. So it's basically the input, right? The input of the sequence. We're saying what happens when you let the input of the sequence go to infinity? If that goes to a number L, okay, so if we get an answer L, so I'm saying here, provided this limit exists, we know in calculus that not all limits exist. If the limit exists, all right, then what we will write is this, and this is real important right here. When you see this right there, what that means is that you've let n go to infinity and concluded that the sequence is getting closer and closer to L, all right? So a sub n with an arrow pointed to a number means that that sequence approaches some value. And we will say, our language here is that a sub n converges to L. Now, if the limit doesn't exist, or the limit goes to positive or negative infinity, we will say that the sequence diverges, or a sub n diverges. So you either, the sequence is either headed to a number, a nice fixed real number, in which case we would say it converges. And in any other case, we would say it diverges. With me? I see everyone writing this down. It's fine if you write it down, but just remember, I will provide this to you later. So my intent is not that you copy everything. Go ahead and try if you like, but I'm going to keep moving. All right, so I have some visualizations here for limits. So take a look at this. This is the problem we just did, basically, right? As you let n go to infinity, so as you start looking at the plots of this sequence, let me scroll down a little bit more. There we go. As you start looking at this sequence going further and further out, they are getting closer and closer to some number without actually getting there, right? And it looks like we said it looks like it's getting closer to 1. So if I were to plot like a horizontal line, y equals 1, you can see that that would be our limit, right? That's what this is approaching, getting closer and closer to. So that's why I write this, okay? So for this, the sequence here is n squared over n squared plus 1, or 1 plus n squared. We could say that that goes to 1, right? This goes to 1 means that if I take the limit of this, it's headed to 1, all right? So what's nice about this notation is that you don't have to write limit n goes to infinity, right? It's understood. You took the limit, you got 1. Now, we haven't actually done the limit by hand. We're just visually saying, oh, yeah, it looks like it's going to 1, right? That's all we're doing. We will do it by hand. Okay, next visual example. This is an interesting one. Look at this sequence. You start out, it's way up here, right? And then it comes down, then it goes down here, then here, then here, then up a little bit, and then down, and then back up, and then back down, and then back up, and then back down, and back up, and back down. So I'm saying here that the limit is 0. Now, in the previous problem, the limit was 1, right? Did we ever reach 1?
No.
No. Okay, so in a limit, do you have to reach the number you're saying you're going to? You don't, but can you reach it? Yes, it is possible to reach it. It's just the difference. It's a subtle difference. For a limit to be L, you either reach L or you get it closer and closer to L the further out you go, right? Here, 0, I'm saying is the limit. And the reason why I'm saying that is because it's almost like this is like the sequence is living within this funnel, and it's getting funneled in between, like, it's just getting smaller and smaller. Even though it's like oscillating up and down, it's getting funneled in. So if you were to take like the absolute value, the distance from the point to the x-axis, or L is y equals 0, that the further out you go, the closer and closer you get to 0. Now, you may hit 0 some of those times, but the further out you go, I promise you that the window is narrowing and narrowing and narrowing. Does that make sense? All right, here's another example. This one's pretty much the same exact problem, not the same problem, but the same idea as the last one. It's like you start out here, and then it goes down here, then up and down, then up and down, then up and down, and it gets funneled into 0. So we say that this sequence approaches 0. So visually, do you understand the idea of a limit? What your sequence has to look like? Right, here's examples of divergence, which would mean that your sequence is not converging. Whoa. Right, look at this one. What does it do? It starts here, goes down, then back up, back down, back up, back down, back up, back down, back up. You cannot tell me that this is approaching 1, right? This is 1 up here. Can't tell me it's approaching 1, because if you go out a little bit more, it's down at -1, right? And you can't tell me the limit's -1, because if you go out a little more, it's up at 1. So there's no funneling of anything happening here. Do y'all see that? So here, as n goes to infinity, a sub n does not approach any one particular number. By the way, this is the graph of -1 to the n. This is -1 to the n, because it spits out -1 first, then 1, then -1, then 1, then -1, then 1, then -1, then 1. Here's another one. Yeah, that's a weird one, huh? Is it converging? No, right? It almost looks completely chaotic. I don't remember where I got that one from. Hold on. Trying to remember here. Oh, it's actually sine of n. That's what it is. Which is really cool, because if you put the graph in there, it's just the sine function, but only at the integers. So that's sine of 1, sine of 2, sine of 3, sine of 4. So if you take the sine curve out, it looks like complete garbage, doesn't it? There looks like there's no order to that at all. But it actually, all those points do live on a sine curve, which is kind of cool. But we can definitely say it doesn't converge, right? Like that doesn't converge because it's just scattered. All right. So visually, convergence and divergence make sense? Here's one last one. This one is kind of, should have been maybe the first example, because as you go out, what happens? This thing just keeps growing and growing and growing. And we don't know for sure what happens out there, but just if we follow the trend, right, and we believe that it continues this, then it's just going to continue off and get bigger and bigger and bigger. So as n goes to infinity, so as we move to the right, the sequence appears to be headed off to infinity, which is not a number. Infinity is not a number. So we would say that this diverges. We good? All right. Now, a theorem. This theorem says, I'll try and make this bigger again for you. Let's say we have a limit as x, oops. the limit, say we take the limit as x goes to infinity of some function back in Cal 1, back, stuff we've done before. Let's say that that function has a limit of L. And if we take, now this part's a little tricky what it means. If we take that function and we restrict it to just the natural numbers, we plug in only 1, 2, 3, 4, 5, 6, right? And call that our sequence, then the sequence must go to the same limit. Okay, so all this is saying is this. Look, if I have a nice smooth continuous function here, let's see the orange function is smooth and that's a good old f of x. If we define a sequence to be that function, but only on the integers, then wherever the function goes, the sequence goes, right? So it's almost like we can look at a sequence, act like it's a function, and then take the limit the way we did in calculus, and whatever that function does, the sequence must follow. This is a really nice theorem because it allows us to do limits of tons of sequences this way. But we have to understand that it's the theorem that allows this, right? And as great as the theorem is, it does break down sometimes. So, okay. So here we go. We've got this sequence sine of n over n squared. Here's an example. Here's an example of this theorem. Okay, here's another example. This is make this a little smaller. So sine of n over n squared. If I were to treat that like a function first, okay, so if I were to take that and say, oh, let's look at the function f of x equals sine of x over x squared, and I were to ask you, all right, take the limit of that as x goes to infinity of sine of x over x squared, what are you going to tell me that limit is and why? What's the limit of this? As x goes to infinity, what's this limit?
0.
Why though? The number on the bottom heads to infinity, right? And the top one, what? Well, as x goes to infinity, sine does what? Think about what the sine function does as you go out to the right forever.
Cycles.
It's up and down, right? But what's important is that it's bounded. Now, my Cal 1 students probably remember, anytime we have bounded over infinity, you've got 0 as the limit, all right? So bounded over infinity, and that would go to 0. Now, that would be, most of my Cal students, that's the way I show them. And it depends on in Cal 1 how you were presented it. But bounded over infinity was one of the big things in my calculus students we talked about. Now, if you didn't have that, you could do some other things like squeeze theorem or something like that. But I think it's sufficient here for us to just understand that as long as the number on top doesn't go to infinity, stays between two things, -1 and 1, then if the bottom gets huge, the ratio should get small. Yes.
You put -1, 1, and then you have sine in the middle, and then you divide that n squared.
Yeah, I'm going to do it in a minute. I'm going to do it for this problem in a minute because I need to formally introduce the squeeze theorem for sequences, and then I'll do it. Okay, but again, the big idea here is that if we can treat this like a function, then whatever the function does, the sequence does as well. Can I proceed? All right, here we go. Squeeze theorem. So the squeeze theorem says, and students, I don't know, the squeeze theorem is weird, okay? It's weird because, I mean, I think most people understand what it is, but actually executing it and doing it is something else. So the squeeze theorem says, let's say you have 3 sequences, okay? You have 3 sequences, A sub n, B sub n, and C sub n, and that they have this inequality relationship. So the A sub n sequence, if you were to graph it, the dots are always smaller than or equal to the B sub n. So the dots of A sub n are always below the ones of B sub n. And the dots of B sub n are always below the dots of C sub n, right? So you have to imagine 3 different sequences where one of them is below the other one, which is below the other one. So you got one in the middle, one on top, one on bottom, right? Like layers of a cake. Now it says here that if the limit as n goes to infinity of a sub n, isn't that the bottom layer? If the bottom layer's limit is equal to the top layer's limit, so if the bottom and top layers are both headed to the same place, well, then the one in the middle has to go there also, right? It gets squeezed between. So visually, here's kind of what we're looking at. So let's just take a moment to understand this. We have three different sequences here. We have a purple one, we have a red one, and we have a blue one. The purple one is a sub n. It's the one that's below. It's the lowest one here. And we have the one in the middle, b sub n. So the red sequence is always above the purple. And then we have c sub n, which is this blue sequence, which is always above everything, right? And notice that if we look at c sub n and a sub n, look what happens to them as we go to infinity. Both of those go to infinity. I mean, sorry, go to zero, right? The c sub n, the top layer and the bottom layer both head to zero. So that must mean that the b sub n has to also go to zero. That's what I say here. If a sub n goes to zero and c sub n goes to zero, well, then the b sub n, if we don't know what it is, now we know what it is. It goes to zero also. So let me show you how you would use this for this particular example, sine of n over n. So what you do is the hard part, Cruz, right, is to come up, you have to figure out what the c sub n and the a sub n are. You have to create the inequality. All right, so we want to know what this does, and let's act like we didn't know. We weren't saying bounded over infinity goes to zero. Let's just act like we had no idea what that does as n goes to infinity. So what we would do to create the inequality is I would start by writing the one thing I do know. And the one thing I do know is that all sine functions, no matter what you plug into them, are always bounded between 1 and -1. And I know that from pre-cal. That's just the fundamental idea behind the sine function, right? So I'm starting with that. And then I look over here, I say, well, I don't have sine of n, I have sine of n over n squared, right? So what I'm gonna do now is divide everything by n squared. So if I divide this by n squared, divide this by n squared, divide this by n squared, then that string of inequalities is still true, right? Because you divided everything by the same thing. Wait a minute, don't you have to worry about inequalities that you have to flip them over if you divide or multiply by a negative? You do, right? If you ever divide or multiply an inequality by a negative number, don't you have to flip it over? You do, right? Why am I not worried about that?
Because it's square.
What's bounded?
Sine.
Yeah, but sine, yes, sine is bounded between -1 and 1, but I came through and I divided by n squared. And I'm asking you, why is it that I didn't worry about flipping over the inequality? Because when you have an inequality, if you multiply or divide both sides by a negative number, you have to flip the inequality. So Austin, what did you say?
You're dividing it all by n squared.
We're dividing
So
by n
it's
squared,
It's
right?
a positive power.
That n squared should be positive, right? So it's not going to be negative, right? I divided by some number squared, so it'll always be positive. By the way, what if it wasn't squared? Would I need to be worried?
If it was odd,
If what was odd? N? You can divide by a negative. I mean, you can divide by an odd number. You just can't. You only have to worry about flipping if you do a negative number. Look, let me go over here and just remind you. If you had negative x is less than 4, okay? And I wanted to know what x is. If I wanted that to be a positive x, I would divide both sides by -1. When I do that, I have to flip that inequality over. Now it becomes x greater than -4. Anytime we do that, right? Anytime we multiply or divide by -1, we have to flip the inequality. What I'm saying here is that because I divided both sides by n, or divided everything by n squared, we don't have to worry. But I asked you, if it was just n, do I have to worry? Because what if n is negative? Don't I have to worry about flipping it? Why isn't n negative? What is n? These are sequences, right? What's n? Natural numbers, 1, 2, 3, 4, 5.
Yeah,
Right?
it
We're
starts
not
at
even worried
1.
about it, right? So we're not worried about the flipping. I just don't want to just like I didn't want to just gloss over that and not think about it. We have to actually think about that, right? So I'm not flipping. And now at this point, do y'all see that I've created the inequality? This is A sub n, which is less than or equal to some other sequence B sub n, which is less than or equal to some other sequence C sub n. So what I need now is to see what is the limit of the two end ones. Let me take the limit of both of those as n goes to infinity. Take the limit of this as n goes to infinity. And what we need for the squeeze theorem to work, what we need is that those both go to the same place. They have to go to the same number, and they happen to go to the same number. Where they go to? 0 and 0. So if these two go to 0, well, the one in the middle then has to also, because it's got to be less than or equal to 0 or greater than or equal to 0. So the only way to be less than equal to 0 or greater than equal to 0 simultaneously is if you are equal to 0. Normally, when we're doing squeeze theorem, if you ever see like a sine or a cosine or something like that, then you want to start with that inequality. You know, cosine is greater than or equal to -1, less than or equal to 1, and then work with it. Okay, moving along. Questions? All right, the next theorem that we have says that if you're looking at a sequence and you look at its absolute value, and that absolute value goes to 0 when you take the limit, right? The absolute value of the sequence. If that goes to 0, then you can conclude that the sequence without the absolute value must also go to 0. So if the absolute value of a sequence goes 0, then the sequence itself goes to 0. Careful, must go to 0. So here's an example. Look at this one right here, okay? This example here. I'm going to do something a little different here. I want to go put this in OneNote. That way I have some record of this. So when I'm looking at this, the sequence I'm looking at here is this sequence here. That's A sub n. So the question is, does that, you know, what is the limit as n goes to infinity of that? Well, what's happening on top? What's -1 to the n? What happens as I start plugging in different values of n there? It just flips back and forth, -1, 1, -1, 1, -1, 1. And what does the bottom do? It gets huge, right? So you could argue right now, bounded over infinity, this goes to 0. The theorem says, though, if you take the absolute value, the limit of the absolute value, well, when you do that, the absolute value of the top, no matter what n is going to be 1, isn't it? So you're going to get 1 over n squared. And we all know that that's 0. I hope we know that, right? Fixed over infinity, that goes to 0. And so what does the theorem now say? It says this, therefore, so have I used those 3 dots? I feel like I have.
No.
No, I'm not. That means therefore you're going to see it. You're going to see this a lot from me. I didn't make it up. That's math. That's actual mathematical symbol we use. Therefore, okay, 3 dots. Therefore, what's the conclusion of this theorem? If the absolute value of the sequence goes to 0, then what can you conclude? The original sequence goes to 0. All right.
How did we know to take the absolute value?
That's what the theorem, how did we know?
Yeah.
Well, because the theorem said if you ever are looking at a sequence and you're not sure what the limit is, then take the absolute value. If it goes to 0, then the original sequence goes to 0 also. Okay. So I said, all right, maybe I'm just not quite sure what this one does. So I took the absolute value of it. Oh, it went to 0. I'm happy. Okay. Let me see. I'm trying to think of one where. Yeah, let's just leave it at that. I don't want to confuse things. Yes. Let me. That's what I was going to do. Let me just come up with one real quick. Okay. how about this one? What if you have a sequence? What if I'm trying to find the limit as n goes to infinity of -1 to the n times n over n plus 1? All right, so what I would do here is I'm trying to figure out what the limit of this is, right? And I see the -1 to the n. So I'm thinking, okay, if I do the absolute value, I don't have to think about that anymore, do I? Right? Like I don't have to, if I say, all right, I'm going to use the theorem. I'm going to take the limit as n goes to infinity of the absolute value of -1 to the n times n over n plus 1. And that right there, I don't have to look at the -1 to the n anymore. So all I have to do is look at the n over n plus 1. Why did I drop the absolute value completely here? The absolute value of -1 to the n, that's just 1, right? And then n over n plus 1, why do I not care about the absolute value anymore? N's are positive, these n's are positive, so I don't need an absolute value, right? So can someone tell me where this goes? Does that go to 0?
Goes to 1.
It goes to 1. Now we're going to need to talk a little bit more about this, but so I'm going to say this goes to 1 right now, but I'm going to leave a question mark, okay? Because we haven't formally talked about why, but that goes to 1. So what does the theorem say? Does the theorem say then that goes to 1? No, it doesn't. The theorem says that if you take the absolute value and it goes to 0, then you can say the original one went to 0. But if it goes something other than 0, the theorem is useless. I don't know if that's what you were looking for or asking for, but the theorem is only useful if the limit of the absolute value goes to 0. If it goes 0, then you can conclude something about the original. Goes something else, you just throw it away. All right. Okay. Here's another example. So all we have right now, okay, all we have right now is the squeeze theorem, right? And then we have the absolute value theorem, but then that has to go to 0 for it to work. All right. This one's a good one. So I just want you to kind of remember what it is that we're actually doing here. It's like somebody gave us a sequence. A sub n is n factorial over n to the n. Now, if I start writing out this sequence, I plug in 1 first. What's 1 factorial? 1 over 1 raised to the 1, right? Which is 1. So that's just 1. Now I plug in 2. What's 2 factorial? 2 times 1, which is 2. And then over 2 to the 2, 4. Plus, okay, now 3 factorial. 3 factorial is 3 times 2 times 1, which is 6. Over 3 to the 3, 27, right? I'll do one more. 4 factorial, 24 over 4 to the 4, right? Isn't that where we are? 4 to the 4, what's that?
256.
56. Comma, dot, 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 right? We have this sequence of numbers. Here it is. Here's the sequence. I would like to know, does it converge to something? What does it look like? Does it look like it's converging to something to you? I mean, these bottoms are getting huge, aren't they? Maybe it's headed to 0. Does it seem reasonable that it is? Well, we need to prove it. Okay. So how do we prove this? So here's what I'm going to do. I'm going to start with this sequence. I'm not going to take the limit yet. I'm just going to look at the sequence itself. What does n factorial on top mean? That means n minus 1 times n minus 2 times n minus 3 times n minus 4. And I keep doing that until I get down to 1. right? That's the definition of n factorial. You give me an n, and what I'm gonna do is take that number and multiply it by the one less than it, then the 1, 2 less than it, 3 less than, until I get down to 1. Now I'm gonna divide that by n to the n. N to the n means n times n times n times n times n. How many n's do I have multiplied together? N of
N.
them. N of them. Okay. Well, if I have n of them, how many of these factors do I have on top? It might help if I write it down. If I wrote down as an example 5 factorial, wouldn't that be 5 times 4 times 3 times 2 times 1 over 5 to the 5? Wouldn't that be equal to 5 times 5 times 5 times 5 times 5? Right? That's 5 factorial over 5 to the 5 would look like this. So for every factor on top, I'd have a 5 underneath it. So if over here I have n factorial on top, below each of these factors, I would have a what? An n, right? I would have an n here times an n there times an n here times an n here times an n here times every one of those would have an n underneath, including the very last one. Agreed? Now, what can you tell me? This is the critical part. What can you tell me about n over n? What's that always going to give you? 1. Okay. What about the next one? N minus 1 over n. Tell me about that number.
It'll be a larger denominator than the numerator.
The denominator is larger than the numerator, which means that ratio should be less than 1, right? Less than 1, whatever it is. I don't know what it is, but whatever it is, it's less than 1. Agreed? So this right here is less than 1. What about the next one? Same thing, right? It's also less than 1. What about the next one? Less than 1, less than 1, all the way till you get the last one. Now, don't go to this one yet. I want you to stop right there. Okay. So we have the first one is 1 times, so we have this n over n is 1. The next number is less than 1, less than 1, less than 1, less than 1, all the way till you get to here. Yes? Go with me? I'm about to do a squeeze theorem. All right. So what I want to do now is I want to say all of this together, all of that together. Would you agree? All those numbers multiplied together would be less than 1, because each one of them by themselves is less than 1. And when you take numbers that are smaller than 1 and multiply them times each other, it just gets smaller and smaller and smaller. So all of this together is less than 1. So we have some number less than 1 multiplied by that first piece, 1 over n, right? Right here. So if you agree that this number, everything here circled in red, is less than 1, and I still have a 1 over n here, then can you, do you buy this? That this whole thing then has to be less than 1 times 1 over n? It's like compare the number in front of the 1 over n here. This is a 1, right? That 1 is bigger than all this red stuff. All this stuff here, right? You just told me that all these numbers together are less than 1. So if I put a number that's smaller than 1 in front of 1 over n, that's definitely less than me putting 1 in front of 1 over n. Yay or nay? This is a number sense thing, so you have to see that. Would you also agree that this whole thing is bigger than or equal to 0? Positive number, positive number, positive number, positive number, positive number, positive, right? These are all positive numbers. So no matter what, this thing has got to be greater than or equal to 0. I've created the squeeze. These are the two things. This is my a sub n. This sequence over here is a constant sequence. It's always 0. And then the c sub n over here is this sequence just 1 over n. And the sequence I'm interested in the middle, right here, all of this is now squeezed between the two. And now what I do is I take the limit as n goes to infinity here, and the limit as n goes to infinity here. And what I get on the right side is 0, and on the left side, well, this is a constant. The limit of a constant is still the constant. These two are squeezed between 0, which means that this whole thing here, right, that whole thing has to head to 0 also.
So for this particular problem, what was the trigger that allowed you to see that that was probably
That the trigger that made me do a squeeze theorem,
yes.
the trigger was that I didn't have another way. And now you know that when you see something with like factorials, like n to the n or something like that, you might think to do something like this. So I'm showing it to you to demonstrate to you how you might want to think now, you know, like why I did it is because somebody showed me, and now I'm showing you, you know. Okay, we continue. A sequence you should know, all right? This is a very important sequence. It's the sequence a sub n equals r to the n, where r is a constant. So you just have some number. This is a lot like an exponential sequence. You know how when we were studying exponential functions, we had f of x equals a to the x. Those were exponentials. And we had restrictions on a. We said a had to be positive and not 1. Here, I want us to think about a sequence r to the n, where r is any number, and we're going to start raising it to powers and take a look at what happens. All right. So I already have the conclusions here. This is the conclusion. But I want you to see these sequences first before we do these conclusions. So I have an animation here ready to go.
Yay.
So here we go. Guess not an animation. All right, so here we go. Right now, I want everyone to understand R is 1. Okay, R is 1. So that means we're looking at this sequence right here. We're looking at the sequence a sub n equals r to the n. So if r is 1, right, then this is really 1 to the n. So our sequence is the sequence 1, 1, 1, 1, because 1 to any power is just 1, right? So there's our sequence, dot, dot, dot. That's a very boring sequence, all right? Just 1, 1, 1, 1. Now, what if r is 2? What's going to happen? 2 to the n. So what if this was 2 to the n? This would be the sequence 2 to the first power, 2 squared, right? It would look like that. Those are going to start blowing up very fast, right? Getting very big. All right. What if we do something like this? 1/2 to the n. That sequence. You plug in 1, you get 1/2. What about 1/2 squared? 1/4,
1/4.
then 1/8, and those are getting small, right? Okay, so on this animation, I can adjust the R. So here we go. I'm going to go with an R bigger than 1. Watch the sequence. Boom, it took off, right? Look, I'm only at 1.05, and that thing just took off. I make it bigger, it's gonna, I mean, it's off the charts, right? I think, yeah, I don't have it where I can zoom out, but you can imagine that thing is gone, right? It's gone. You know, I think I did this in Desmos also, and it was a little bit better. Let me bring it in Desmos. Where is it? Yeah, here we go. Adjust it here. So here's, yeah, there's R is 1.06. That sucker's gone. All right, it took off, which means that the sequence, this sequence diverged, right? It diverged. It took off to infinity. All right. Now let me adjust it. Let me go it back. Let me get it to 1. There's 1, and you know, I only have it going out so far. So there we go. That's 1. So it's just flat. And then now let's do something like 1/2 or something. And then look at that. See, if I did like, it's right now it's 0.78. And look, that's converging, isn't it? It's going, get smaller and smaller. It's approaching 0. In fact, if I change that R, any numbers here, right? Any numbers here, as long as they're smaller than 1, what happens when I go negative? Okay, so it's hard to tell what happened here. It's hard to tell what happened here. but you've got positive number, negative number, positive number, negative number. Because when you take a negative number and raise it to powers, right, it's either going to turn out to be positive or negative, depending on if it's even or odd up there. So if I'm plugging in a negative number like negative 0.18, y'all see I still have convergence. I might go back to mine again. I think mine might have been better for this. If I go and yeah, see, look at between, right now I'm 0.78. You can see the convergence there. Go negative. Yeah, see negative, you can see how they're alternating, but see they're still converging until I get to where? What's going to happen at -1? What am I going to see? I'm going to see that one thing that we had earlier, which was there, that one. Divergence, right? As soon as I get to -1, divergence. If I go a little bit to the right of it, what do I have? Convergence. It's slow, but it's funneling in. Do y'all see that? And then once I go past -1 to the left, I get divergence, and then it starts taking off in both directions like that. The n is staying. The n is, wait, say again. Let me make sure I understand your question.
All the R is moving on the graph like that, and that's without changing the n value.
Well, each of these points comes from R. Okay, so like, let's just go. Let me make sure you understand this. You go to, well, that's too big. Right now, R is -1.07. Okay, so when I plug in 1, right? When I plug in 1, 1 is right here. Actually, can't see it, but 1's right here. If I plug in 1, what's this number to the first power? Itself, right? So that's -1. That's this number right here. Now I plug in 2. When I plug in 2, you square that, and that's this number.
Okay.
Then you plug in 3, and then that's this number. 4 is that, 5, 6. So the plot represents that number raised to all these different powers. And we're trying to see what happens as you go out. All I'm doing on this is just adjusting the R to kind of verify or visually convince you that if R is between, if the absolute value of R is less than 1. So as long as R is between -1 and 1, you will have convergence to 0. All right. Now, if R is 1, you're just going to get 1, 1, 1, 1, 1, 1, 1, 1. Now, if it's anything else, it's going to diverge.
Yeah, that makes sense. In my head, n was 1 value the whole time. So
Oh, okay. Yeah. All right. We good? We're getting to the point here where we're going to actually start doing some problems. So we need some more definitions, though. Yes.
On the last one, where you did this one, why'd you put 1/n right here?
Yeah, I got you.
Greater than 1 times 1/n.
Okay, because when I was asking you to look at everything I circled there, right? All of this stuff that I circled, I had left off, I did not include that piece right there.
Okay.
This 1/n, I said, just ignore that for right now. And let me convince you that all of this to the left of it is less than 1. So the stuff in this is this, right? And then everything here, you said you agreed, everything in green was less than 1. This 1/n, I don't want you to do anything with it, leave it alone. So if this number in front of this is less than 1, then the whole thing must be less than 1 times 1/n.
The same thing.
This is the same. This 1/n, sorry. This, come on. I don't know what the hell's going on here. That right there is the same as this.
Oh, but that one's less than greater than.
This one, this in green is less. It's like me writing this down. If I write 5 is less than or equal to 5, do you agree with that? Okay. Now, if I write 2 times 5 is less than 3 times 5, you would agree with that because this number, right? This number 2 is smaller than that number.
Yes.
That's exactly what I'm doing here. This is like the 5 and 5, and I'm saying this number here is smaller than that number there. This is like the 2 and the 3 just were.
Okay.
That make more sense?
Yeah, that's better.
Okay.
And how did you know about the bounded on sine? Sine of x is bounded?
How do I know? Well, I wrote that sine of n, I said this was bounded, right?
Yeah.
When I said bounded, it's because it's always between -1 and 1,
Right.
right? So that's what I mean. Bounded means that it's always between two numbers.
Oh, okay. Thank you.
We're going to talk more about that right now, actually.
Yeah, that's on the formula sheet.
Mm-hmm.
Yeah.
All right, the next definitions are, I realize this is kind of like, come on, I realize that, but I mean, we have to have this foundation or else the rest chapter is going to be a disaster. Okay, we have to understand this whole idea of sequences and convergence and increase, decrease, all this stuff. We have to have an idea of what it means. So a sequence is said to be increasing if a sub n is less than a sub n plus 1 for all n greater than or equal to 1. Okay. The picture of an increasing sequence every student can look at and understand, right? Look at this purple sequence. As you move from left to right, it goes up. It's increasing, right? But this inequality is the important thing. What we're saying is that if you pick some n, it doesn't matter where it is. Let's say you pick an n, see on the bottom here, I pick this n. If I go to the sequence and I go up here, that's going to correspond to that dot, right? That's a sub n. That to be increasing means if I go to the next one down, n plus 1, then that dot should be, well, actually n plus 1 is a little closer, but the next one down, that's not going to work. N plus 1 is a lot closer than that. If this is n plus 1 is the next one. I plug that in, I'm at this dot. And what is the relationship between these two dots? The one on the right must be bigger than the one on the left for us to be increasing. And that's what this inequality is saying. A sub n plus 1 has to be bigger than a sub n for us to be increasing. Decreasing is the opposite. And that's this picture. If I were to pick a point here, a sub n, right, a sub n, plug in n, then if I plug in n plus 1, the one right next to it, the one right next to it has to be below it. So a sub n has to be bigger than the next one down. And it has to hold the whole way, and you get decreasing. Make sense? Questions? We're good? Yes.
There's four versions of it, right? There's the strictly one, and then there's the regular one. Do we ever use the regular?
Here in with sequences, we just talk about increasing and decreasing as being strictly, yes. So it can't ever be equal. It has to be always going up or always going down. All right, now, once we have the idea of increasing and decreasing, oh, I forgot one thing here. Subtle little thing here, but it's here. Either way, okay, whether or not if your sequence is increasing or decreasing, either way, we call it a monotonic sequence. Monotonic. So if I tell you right now, hey, I have this sequence and it's monotonic, can you tell me whether or not it's increasing or decreasing?
No.
Which one it is? If I just tell you it's monotonic, can you tell me which one it is increasing or decreasing?
If it's greater than a n,
You would have to inspect it, right? But if I just tell you, hey, I have this monotonic sequence, here it is. You can't tell me if it's increasing or decreasing. Monotonic means it's going to be doing one or the other, all right? So monotonic is like a general way of saying it's doing one of those two things, all right? Now, if you say it's monotonic increasing, then you know which one it is, right? Monotonic decreasing, you know which one it is. That's an important term here. We're going to use it in a minute for a theorem.
Is saying monotonic increasing or decreasing redundant?
It is kind of redundant, yes, but it is used. You'll hear it. Well, I mean, if you're a math major, you'll hear it. You'll see it in different textbooks. They will say monotonic decreasing. If you just said decreasing, that would kill everything. That would take care of it. You don't need to say the monotonic. All right, so here's an example where we're given a sequence and we are asked to show that this is eventually decreasing. Here's what we're not going to do. We're not going to just start listing out the sequence. Okay? That is not what we're going to do, because a lot of students will like, oh, okay, let me just plug in n is 1 and 2 and 3 and 4, and just let me show that the numbers eventually start getting smaller than one another. Like each time I go out, it gets smaller. That would be not enough. All right. You have to show it using the definition. So here's where the first time in this chapter, where we're actually going to have to use a definition and do like almost, it's not a proof, but we're going to start writing as if we're going to have to be a little bit particular about what we're saying, what we're trying to show, and stopping when we've shown what we're trying to do. All right. So I always like to start these things off by writing down what it is that I'm trying to show. All right. So I'm going to write down, I want to show. Now, I don't like to write want to show over and over and over. So from now on, you'll see me write WTS for want to show. All right. So what is it that I need to show? I want to show you that this is eventually decreasing, right? So that means I want to show you that eventually A sub n is what? Decreasing means that as I'm moving from left to right, A sub n, the one next to it should be what? Below it, right? So this A sub n should be bigger than the next one. So I want to show you that A sub n is bigger than A sub n plus 1, right? Eventually that happens. All right, here's the part that students kind of have a little bit of issue with. What is A sub n? Well, they gave us a formula for A sub n, didn't they? It's right there. It's 10n over 2n plus 1. I want to show you that that's bigger than the same sequence function, but one later, right? One later. So that means I'm plugging in n plus 1 into this instead of n, right? So that's fine. I just replace all the n's with n plus 1s everywhere I see it. Everywhere I see an n, replacing with 2n plus 1. So I'm trying, does anyone have any questions what I just did? I replaced all the n's in the original sequence with n plus 1s. Right? That's all I did. And here, just A sub n is just the original sequence. I want to show that this is true. I need to show you that that's true. I need to prove to you that that's true. Right now, what I have written, I don't think you're convinced that it's true. I mean, I wouldn't be convinced it's true. I have to actually prove this. So this is almost like a question. Is it true? Is that true? If it is, then it's decreasing, right? So now it's just algebra. So first thing I'm going to do here, I'm going to just clean things up. This is 10n over 2n plus 1 bigger than, I'm going to distribute the 10 through on top, 10n plus 10 over 2n plus 3. Where did I get 2n plus 3 from? Distribute the 2, right? And then collect the 2 and the 1 together to get 3. Okay, so this right here, again, you cannot tell me that this one is smaller than this one. You can't. You cannot give me the argument that, oh, wait, 2n plus 3 is bigger than 2n plus 1. So this denominator is bigger than that one. So yeah, this one's smaller. You can't say that because this numerator is bigger, isn't it? That numerator is bigger than that one. So that's okay. We're just going to continue with algebra. I'm due like to cross multiply now. Okay. So I'm going to take 10n times 2n plus 3 greater than 10n plus 10 times 2n plus 1. By the way, do I have to worry about flipping the inequality? Because remember, we multiplied both sides of the inequality by a number. Are you concerned that that number might be negative? In this case, no, right? Because 2n plus 3, that should be positive because I'm only plugging in, 1 or 2 or 3 for n. Same thing with this. 2n plus 1 should be positive. Let's go ahead and distribute. And on the right side, we'll have to do that, like expand or FOIL out. So we should get 20n squared plus, what's that, 30n? Bigger than 20n squared plus 20n squared, and then 10n, and then 20n, I get another 30n, and then plus 10. You'll agree? And now I'd like to get everything over to, let's get all the n stuff to one side. And do y'all see what starts happening? We start subtracting, like let's subtract 20n squared. Let's subtract 30n from both sides. I'm missing something, no? What am I getting here? 20n squared. What is going on? What is our result here?
0 is greater than 10.
0 is greater than 10. Wait a minute. Something ain't right. 0 greater than 10? 0 is not greater than 10.
Oh.
Right? Right? I mean, this is a problem, right? This is a problem. So what have we done? We were trying to show that it was eventually decreasing, right? So we tried to show that when you look at a sub n and you look at the one next to it, right? That the first one should be bigger than the next one. Well, when we set up that inequality, at the end, we got a statement that's nonsense, right? Which means that this can't be true, right? In fact, this thing looks like it's increasing.
Contradiction.
Right? It looks like it's increasing. So when I said show that this is eventually decreasing, we tried to show this, but if I had said this instead, increasing, right? Then what would have changed? The what
That's
I
the
wanted
sign.
to show would have been what? A sub n is less than a sub n plus 1. And then we would have done the exact same work. And at the end, we would have got what? 0 is less than 10, which would have been true, which means that I would have been able to show that it's increasing, right? Understand? Which means that when I typed this up last night, I screwed it up. So I apologize. I was watching the game and I was trying to get all this done. So it's all right. Let's just change it to increasing. But this is a good exercise because you could see that when we tried to show it's decreasing, we got this thing that doesn't make any freaking sense, right? And so if that doesn't make sense, then that means that's not what it's doing. So change that to increasing and then just go back and change all these inequalities the other way around. And you should get a true statement at the end, right? This is true. And as soon as you get a true statement, you have shown that it is, in this case, increasing. I'm gonna have to change that in the notes. Increasing. All right, last definitions and then a theorem. So bounded sequences. A sequence is said to be bounded above if there exists a capital M such that a sub n, the sequence, is always less than or equal to that M. So here's a picture of what it means to be bounded above. You see this sequence in blue? Do you see this number, capital M, up here? Do you see that this blue never goes past that? Then we would say that M is an upper bound of that sequence. All right? Is that the only upper bound of this sequence? Could I pick another number that's above or equal to this? Sure, I could have picked, this is 1. I could have picked 1.5, right? So a bounded sequence, the only condition to be bounded, to have a sequence and say it's bounded, is that there's some number it never gets past. Okay, it doesn't really matter. It could be multiple numbers it doesn't get past, but there has to be at least one that it doesn't get past. Bounded below is the opposite, right? The sequence always stays above some number, never goes below this. This would be called a lower bound. And of course, there could be multiple lower bounds. So bounded above, bounded below. Most students look at that and they have no problems with the idea, right? Bounded above, bounded below. Now, if a sequence is bounded above and bounded below at the same time, then we call it a bounded sequence. I don't know, my brain is always not liked this, because look at the definition up here, bounded above. All right, bounded above means you have a sequence and then the top can't go past, right? We would not call that a bounded sequence. That would be a bounded above sequence. And then a sequence that's bounded below, you would not call that a bounded sequence. You would call it a bounded below sequence. You have to be very specific. To say a sequence is bounded is a very strong condition. It means it's bounded above and below at the same time. So that's just the language we use, the definition we use. And so here's an example of a bounded sequence. This is that sine n one that I showed you earlier today. So this sequence, notice that the sequence is always stuck between two numbers, no matter what. And so therefore it's bounded. This goes back to like that sine n is between -1 and 1. Okay. Last theorem. The monotonic sequence theorem. This is a really nice result of everything. Every bounded monotonic sequence converges. Every bounded monotonic sequence converges. So think about this. You have a sequence that's bounded, right? Let's say you have a sequence that's bounded. That means it's stuck between two numbers, right? And then I tell you it's monotonic. What does that mean? It's either increasing or decreasing, one or the other, right? Well, either way, let's say it's bounded above and below, right? Which means it's bounded. Let's say it was increasing. Then it has to continue going up and up and up and up and up and up, right? But it's bounded above, which means it has to flatten out. And it can't come back down. Why can't it come back down? Because it's increasing. So it's monotonic. It cannot turn back. So if it has to keep going up and never get past a number, then it has to asymptotically approach something, which means that it's converging to something. And then the same argument could be said for if it was decreasing, right? Now, the thing about this theorem is, what's good about it is it'll tell you whether or not a sequence converges or diverges, but it doesn't tell you what it converges or diverges to. I mean, sorry. Let me completely restate that. What this theorem tells you is whether or not a sequence would converge, all right? If you've got bounded and monotonic, you've got convergence, but it doesn't tell you what it converges to. It just tells you that it does. All right, that is it for the notes for this section, and now it's exercises. So what we're going to do, we still have time here, is I'm going to pick a couple of these to try. So on these first ones here, this is straight out of the ebook. It says determine whether the sequence converges or diverges. If it converges, find the limit. All right. So let's just start cranking some of these out. I'm gonna grab some of these. I know this is homework. I know some of you have already done some of this, but okay, let's take a look at number 9. I want to know if 9 converges or diverges. So I'm going to take the limit as n goes to infinity of 1 minus 0.2 to the n. Okay, does that converge or diverge? And why? Do you recognize this? That looks like r to the n, right? We talked about this today, r to the n. We said that that would converge to 0 if what? If the
Less
numbers
than
between
1.
-1 and 1, that will converge to 0, won't it? If it goes outside of 1, it diverges. Do I need to show you all the picture again? No? This goes, so this whole thing goes to 0, and then I have 1 minus that, so that goes to 1, right? What if this had been 1 minus 2 to the n. It would diverge, okay? It would diverge. If this was 2 to the n, it would diverge. All right, let's look at the next one. I want to take the limit as n goes to infinity of n cubed over n cubed plus 1. All right, where does the numerator go as n goes to infinity?
Infinity.
Infinity. The bottom also goes to infinity, right? You have infinity over infinity. Infinity over infinity. And in Cal 1, how did we handle that? When you had infinity on top and infinity on the bottom, how did we handle that? L'Hopital's rule, right? L'Hopital. But hold on, time out. Don't get too excited. Hold on. L'Hopital's rule required differentiation, didn't it? A derivative. Derivatives, if you go back to Cal 1, differentiability implies continuity. There was a big theorem that said if you're differentiable somewhere, you must be continuous somewhere. What's wrong with that?
Sequences are not continuous.
Sequences aren't continuous. You cannot take the derivative of a sequence. You can't. You're not allowed to. All right. You're not allowed to take derivative of a sequence because it's not a continuous function. However, we had this really important theorem early in today that said right here, it said if we can look at the sequence as a function, right? Whatever the function does, the sequence does, right? Which means we can use L'Hopital's rule on the function, figure out then what that function does, and then just say, hey, the sequence follows it. Make sense? So when I go to do this right here, technically, now this is technically, I'm not going to do it, but just to make sure you understand, technically what I'm really doing here is I'm doing the limit as x goes to infinity of x cubed over x cubed plus 1, right? I'm looking at it as a function of x, then doing my L'Hopital's rule. So L'Hopital here, what's L'Hopital? If we have infinity over infinity or 0 over 0, we do what? Derivative of the top over the derivative of the bottom. So derivative of the top is 3x squared, derivative of the bottom, 3x squared. Hey, algebraically, those just go away and they just become a 1. So this limit is 1. So according to the theorem that I just showed you a second ago, whatever the function does, the continuous function does, the sequence follows, right? So that means I can conclude from that, therefore, this limit as n goes to infinity of the sequence, must also go to 1. Because the function went to 1, the sequence goes. I just don't want you to start pounding away with L'Hopital without understanding that sequences can't be differentiated. It's impossible to talk about the slope of a tangent line of a point, of a dot sitting somewhere in space. Yeah. That's right. When we convert it, see, when we have this written, we're saying n can only be what? 1, 2, 3, 4, 5, 6. But when we convert it to this, now x can be any number, right? So when you graph that, it's going to be a nice smooth curve, which we can differentiate. The n represents, well, I don't want to use continuous for anything. I don't want to confuse it with continuity in Cal 1 means basically you can draw it without picking up your pencil. A sequence, you have to pick up your pencil the whole time you draw it because it's just dot, 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 right? So I always think of a sequence as basically taking a function and looking at just certain values on that function at the integers, 1, 2, 3, 4, 5. Which is a good way to think about sequences, but then later on you realize that there are some sequences that there are no functions for. Like there's no equivalent to it in like a continuous function. All right, let's do 11. Well, you might be able to handle 11. Wouldn't that also give you infinity over infinity? So you can convert that to f of x again and do L'Hopital? Okay, I'll let you do that one on your own. Let's see what some of these others look like. Some of these get pretty weird. All right, so look at 13. Look at 13. So if I take the limit of this one, okay, if I take the limit of this one, can I convert it to a function of x? I should be able to. I should be able to do the limit as x goes to infinity of tangent of 2x pi over 1 plus 8x. And then I could let x go to infinity. So when you let x go to infinity, you get tangent infinity over infinity again, right? Because 2 times infinity times pi is infinity, plus 8 times infinity plus 1 is infinity. So we have infinity over infinity. So we can do L'Hopital here. And you only have to do L'Hopital on the inside of that tangent function. What's the derivative of the top? 2 pi, and then over the bottom is 8. That's pi over 4. What's tangent of pi over 4? One.
1.
Good. So that limit is 1. Okay, let's keep going. I got to move quick here. How about this one? Could I look at that one as a function of x? I think we can, right? It's just an exponential function. Anytime I can get these to functions of x, I'm going to go for it. What do we get there? Infinity over infinity again?
Yeah.
And hold on, I don't want to do L'Hopital. I do, but I don't. I do what I don't. Let's hang tight. Time out on the L'Hopital. I think there's an easier way. Why don't we do this? Can we rewrite the sequence like this? Okay, so that's the original sequence, right? Like that. Just properties of exponents. Do you see that both of these are to the n? So couldn't I rewrite this as 3/5 to the n times 9? So just rewrite the 3 squared as 9 and just make that 3/5 to the n like that. Now, do you know what that does? What is this? R to the n, right? R to the n, where r is between -1 and 1. So that goes where? 0, and 0 times 9 is 0. So this heads to 0 times 9. So that converges to 0. This 3/5 is like an r, right? That's like r to the n. Now, if you would have stuck with the L'Hopital's rule, if you would have done it, I'm just going to show you what would have happened. If you would have stuck with L'Hopital, you would take derivative of the top, and that would have been kind of messy because it would have been derivative of 3 to the x plus 2 is itself times natural log 3 over a derivative of the bottom, which is itself times natural log 5. I mean, yeah, natural log 5. And you're really not getting anywhere here with these derivatives. You would have to break this up and then put the 3 to the x or 3 to the 5th together at some point.
How is it that 3/5 then became 0?
Okay, so one of the main things again today is this whole idea of r to the n, right here. If you ever have r to the n, if the absolute value of r is less than 1, then this is going to head to 0. This was this picture, right? Give me different values of r. It's either going to converge or diverge, right? And the r in there was the 3/5, and that's smaller than 1. So that must go to 0, right? It goes to 0. -1 and 1. That's what, when you say the absolute value of r is less than 1, when you say absolute value of r is less than 1, that's the same as saying r is less than 1 and greater than -1, right? Because you're within 1 of 0. You're within 1 each way. I'm sorry. Stop. I can't stop it. Okay. All right. I think 15 and 16, those you can do. I'll let you mess with those. There's nothing there that is outside of like calculus stuff. I want to get to something more interesting. Let's just talk through, you know what? Let's grab this one. Okay, there we go. All right, look at this one here. Where is this going? So do we all understand what this piece is doing? What is that doing? Alternating it, right? Back and forth, positive, negative, positive, negative. So really, I'm real concerned about what this does, right? So can you all tell me just by looking at that, what that goes to as n goes to infinity? It's infinity over infinity, right? Do L'Hopital in your head real quick. What are you going to get? If you turn that into a function of x, right? You did the limit as x goes to infinity, and you did L'Hopital, you would get limit x goes to infinity of 1 over 1 plus 1 over 2 root x, right? That's what you would get. And as x goes to infinity, what does 1 over 2 root x go to? 0, right? It's fixed over infinity. That goes to 0. So you just get 1, right? So everything in blue here is going to 1. Y'all agree? And then the green is making it do what? Plus or minus. Is that converging? No. Right? It's diverging. So that thing is headed like up to, it's trying to get up to 1, then down to -1, back up to 1, down -1. So this diverges. The only way to really see that is to actually work that out and then write out, you know, what's happening. This blue part's headed to 1, and then the green part is making it alternate. I have to go fast because we only have so much time here. What about 19? Cosine of n over 2. What's the limit as n goes to infinity? N over 2.
It's bounded.
Well, what if the 2 wasn't there? And I asked you, what's the limit as n goes to infinity of cosine of n? Can you imagine what that looks like? Cosine of n does this, right? But it's just all the dots, right? All the dots within cosine n. Is that converging? No. What does
No.
dividing by 2 do? It changes like the frequency of it, but it's still dots everywhere. Y'all understand that? So this is really like almost saying, what is cosine of infinity? Infinity over 2 is still infinity. And that we're going to be oscillating, but then it's just dots all the dots along this oscillation. And so this limit, this diverges, this sequence diverges also. Look at that compared to number 20 though. On 20, what's happening is n goes to infinity. This is going where? 2 over n goes to 0, right? And what's cosine of 0?
1.
1. That sequence goes to 1. It converges. Slight little difference, right? N over 2 versus 2 over n makes a huge difference in what's happening. What about this one? 2n minus 1 factorial over 2n plus 1 factorial. Well, if n goes to infinity, the top gets infinitely big, right? The bottom gets infinitely big. You cannot use L'Hopital. Why? Because factorial. Think about this. Factorial the factorial function only exists for non-negative numbers. 0 factorial, 1 factorial, 2 factorial. We cannot convert factorial into a function of x to use L'Hopital's rule because there is no function of x that's equivalent to a factorial. So we are not allowed to go L'Hopital here. So the way to do this problem is this. You take the limit as n goes to infinity of the sequence, 2n minus 1 factorial over 2n plus 1 factorial. And then you use the properties of factorials. Watch. This is the limit as n goes to infinity. All right, the top is 2n minus 1 factorial. Watch what I do to the bottom. The bottom is 2n plus 1. I'm going to start writing out what it means. 2n plus 1 times what? What's the next piece?
2n.
2n. Then what's the next piece?
2n minus 1.
1. And then keep going, right? And if I keep going, that's factorial. What I'm saying is this 2n minus 1 factorial is the same as that 2n minus 1 factorial. And so they cancel. And you get 1 there. And so you have 1 over 2n plus 1 times 2n. And now let n go to infinity. And what do you get? 0. So it converges to 0. If you're having problems with that little thing, what I did with the counseling. If you're having problems with that, go get some counseling. No, canceling, think of it this way. If you had 8 factorial over 10 factorial, you could rewrite that as 8 factorial times 10 times 9 times the rest, 8 down would be 8 factorial. So this cancels with that. That's exactly what I just did. All right, let me see what else we have here. Those are interesting. You might have to bring up your calculus notes for some of these to see how it goes. Okay, I think that that's it. I want to leave you to the rest of this to see how you do with it. Ooh, that one's a good one. You know what? We have enough time. Let's just look at this one real quick. It wants us to figure out what this sequence, if it converges or not. Here they don't give you the formula, right? They just give you the sequence. Square root of 2 times the square root of 2 square root of 2 times the square root of 2 times the square root of the 2 square root 2. Ooh. And on and on and on. Does this converge or not is the question. Seem weird? Yeah. Okay, so let me just rewrite this and let's see if this makes some sense. This is 2 to the half power. Agreed? That's the first one. Now the next one is, well, it's the square root of all this, right? So that's the half power. And then inside I have 2 and next to it times 2 to the half again, right? Isn't that what that second one means? Let's try the third one. It's a square root, right? And then I have a 2 here. And then times this right here. Isn't that the previous one? Which is all this. 2 times 2 to the half to the half. Ooh. That looks messy. Okay, let's try and clean these up. This is 2 to the half. This next one is, if I put these two together, it'd be 2 to what power?
To the 3/2.
3 halves, right? 3 halves, and then to the half. I'll go a little slower. This is 2 to the 3 halves. Then I'm going to do it to the half. Over here, let's do that. It's 2 times 2 to the 3 halves to the half, and then I still need all that to the half, comma, dot, dot, dot. This keeps going. All right, what's 2 to the 3 halves to the half? 2 to the 3/4. Okay, here, this will be 2 times 2 to the 3/4 to the half. Put these two together. Mm, 7/4. These two together, 2 to the 7/4. To the half, right? 2 to the 3/4. This next one is 2 to the what? 7/8. Oh, I forgot the 2. 2 to the 7/8. Right? Geez. Am I missing an exponent where? What? I can't hear. Oh, I missed the 1/2. Thank you. Sorry. I don't know why I dropped that. I was just going too fast. Thank you. 2 to half, 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 half. And then these I put together. This was a little more involved, but here's where we are. Do you have a guess as to what the next one is? Do you see a relationship between the numerator and denominator of these fractions? What's the relationship? The top looks like it's always 1 less than the bottom. But what are the bottoms? Do y'all recognize 2, 4, 8? Not 2, 4, 6, 8, 2, 4, 8.
Powers of 2.
Powers of 2, right? So the next one's probably what? The next one we probably would guess would be 2 to the 15/16. And trust me, if you go work this out and follow that same pattern with the roots, you'll get that. So if that's the case, can you give me the sequence function for this? It'd be 2 to the
To the n plus 1 over n squared.
this will be n, this will be n, hold on, 2 to the n. Right, so you're always taking 2 and you're raising it to the bottoms are powers of 2, right? 2 to the first, 2 squared, 2 cubed, and the numerators are always 1 less than that. That is the formula for that sequence. Now, what you need to do is take the limit as n goes to infinity of it, which means you would have to look at this piece, and then I would split it up into 2 fractions, and then take your limit, and you should get a nice clean answer. This converges to 1, but you should show that. Wait, sorry, it converges to 2. All right, look, we're out of time. We have to put this section to sleep, all right? We have to move on. The next section we're going to be starting is next class. Very important class is, where is it? Come on. We are starting next time, series. Okay? So make sure you do your homework for that, and if you have any questions on the take home, just let me know. Have a good day, everyone. Sorry that today was real like definitions, and it won't be like that from here on out. It'll start to feel more mathy. Mhm.
Are you still gonna regrade the exam too? If we turn in the second part?
I have it. I have not regraded them. Those are kind of like in reserve when we get to our final exam. That's going to be something that I'm going to, if you're sitting there going, man, I just need like 3 points, you know, it's like this thing I have in reserve. Yeah. Because I told y'all that if you do well and progress, I will somehow let the final exam either like do something to improve that grade. I already told you a whole class that.
Okay.
So until that happens, I don't want to go and regrade that to do anything to change that grade.
Okay.
Does that make sense?
Yeah,
I want everyone shooting for like way up before I do anything to that exam grade.
thank you.
All right. Dropbox. Yep.